You think you know why the sun shines. Nuclear fusion. Hydrogen turns into helium. Sounds sensible, but if you actually sit down and do the calculation, you find out something disturbing. The sun should not be shining at all. According to the laws of classical physics, the sun should be a dark, cold ball of gas. No light, no heat, no warmth on your face in the morning. The temperature in the center of the sun is about 15 million degrees. Now that sounds hot. But in the world of nuclear physics, 15 million degrees is actually freezing cold. It is not nearly hot enough to push two protons together. Not even close. The electrical repulsion between them is so strong that at 15 million degrees, the protons just bounce off each other, every single time. So the question is not why is the sun so hot? The question is why is the sun not dark? Why is there light? Why are we here at all? Nature cheats, in a way so absurd, so contrary to common sense, that if I just told you the rule, you would not believe me. Nature is strange. It is far more imaginative than we are. Let me show you what I mean. Let me define what I mean by freezing cold. In nuclear physics, temperature is just another way of saying speed. The hotter something is, the faster its particles move. And the faster they move, the harder they slam into each other. For two protons to fuse, to actually touch and stick, they need to overcome what physicists call the Coulomb barrier. Think of it as an electrical wall. Both protons are positively charged, and positive repels positive. The closer they get, the harder they push apart. To climb over that wall by brute force, you would need a temperature of roughly 10 billion degrees Celsius. That is about 18 billion degrees Fahrenheit. The sun's core? 15 million degrees Celsius, around 27 million Fahrenheit. That is roughly 1,000 times too cold. Not a little too cold. Not close, but not quite. A factor of 1,000. Off by 3 orders of magnitude. So here is the question you should actually be asking. And it is not the question your textbook taught you. The question is not, why is the sun hot? That is not an answer. That is a distraction dressed up as an explanation. The real question is, why is the sun not dark? Because according to everything we know about electricity, about classical mechanics, about the behavior of charged particles, it should be dark, cold, dead. And yet, look outside. The sun is there. Something is breaking the rules. And whatever that something is, it is not small. It is not a minor correction. It is the reason anything exists at all. This is not abstract physics. This is about whether you, personally, specifically you, have any right to exist. Whether the carbon in your bones, the oxygen in your lungs, the iron in your blood, had any business being forged in the first place. Because every heavy element in your body was made inside a star. And if stars cannot shine, those elements were never made, and you were never born. So, how does nature cheat? Before I answer that, I need you to understand something about the world you think you live in. Do something for me. Push your hands together. Right now. Press them flat against each other. You feel that? That solid wall of resistance? Skin against skin, bone against bone. You would swear that your hands are touching. They are not. Your hands have never touched anything. Not once. Not ever. Not in your entire life. Here is why. An atom is almost entirely empty space. If you took a hydrogen atom and blew it up to the size of a football stadium, a full-sized NFL stadium, 100 yards across, the nucleus, the proton, would be a marble sitting on the 50-yard line. One marble in a stadium. Everything else? Nothing. Just empty space. And your body is made of atoms, trillions of them, and every single one is almost entirely nothing. So if atoms are mostly empty, what are you pressing against when you push your hands together? Not matter. Not stuff. Not solid things bumping into solid things. What you are feeling is electrical repulsion. The electrons on the surface of your left hand and the electrons on the surface of your right hand are both negatively charged. Negative repels negative, and when you push your hands together, those electron clouds push back. Hard. That is what solidity is. Solidity is not a thing. Solidity is a force, an electromagnetic force between charged particles that are nowhere near each other. And here is how absurdly strong that force is. When if you could somehow strip away just 1% of the electrons from your body, one lousy percent, the electrical charge left behind would be strong enough to lift the entire Earth. Not a rock, not a building, the Earth. All 6 sextillion metric tons of it, about 13.2 sextillion pounds, lifted by a charge imbalance you cannot even see. That is the force your hands are fighting right now. And that is the same force, the exact same electromagnetic repulsion, that stands between 2 protons inside the sun. 2 tiny, positively charged particles trying to get close enough to fuse, and the closer they get, the harder that wall pushes them apart. So now you have felt the problem, literally, in your own hands. Let us go back to the sun. Inside the core of the sun, the temperature is about 15 million degrees Celsius, 27 million degrees Fahrenheit, and at that temperature, hydrogen exists as plasma. No atoms, no electron clouds, just bare protons flying around at enormous speeds, slamming into each other billions of times per second. And here is the thing. For the sun to shine, some of those protons need to fuse. They need to get close enough that the strong nuclear force, which only works at incredibly tiny distances, can grab hold and stick them together. But between here and there, that electromagnetic wall. Let me give you an analogy. You know those little magnets on your fridge? Now take 2 of them and try to push the same poles together, north to north. Feel that rubbery resistance. The closer you push, the harder they fight back. Now imagine those magnets are 1,000 times stronger, 1,000,000 times stronger, and you are trying to push them together with your bare hands. That is what protons face inside the sun, and they are not pushing with hands. They are pushing with speed, with kinetic energy, which physicists just call temperature. Let me be precise about that, because this is one of those words people use without really knowing what it means. Temperature is not a feeling. Temperature is not hot or cold. Temperature is a measurement of how fast particles are jiggling. That is it. The faster they move, the higher the temperature. The slower they move, the lower. So when I say the sun's core is 15 million degrees, what I really mean is, the protons in there are flying at about 500 kilometers per second, roughly 310 miles per second. That sounds fast, and it is fast, in everyday terms, but it is not fast enough. Here's another way to see it. Imagine a bowling alley, and at the end of the lane, instead of pins, there is a hill, a steep, tall hill, and your bowling ball needs to roll up and over that hill to reach the other side. But your ball is too slow. You roll it, and it gets halfway up, and gravity pulls it back down. Every time. You try again. Too slow. Again. Too slow. 1,000 times, 1,000,000 times, 1,000,000,000 times, every single time the ball rolls back. That hill is the Coulomb barrier. And those bowling balls are protons. Now I want you to do something. Hold your fist tight. Squeeze it as hard as you can. Feel that tension? That pressure inside your knuckles? That is what a proton feels when it slams against the Coulomb barrier at 500 kilometers per second and gets thrown back. Every ounce of its kinetic energy, absorbed, reflected, wasted, and it has to do it again, and again, and again. Now let me give you the actual numbers. To climb over the Coulomb barrier by brute force, no tricks, no shortcuts, a proton would need to be moving at a temperature of about 10 billion degrees Celsius. That is roughly 18 billion degrees Fahrenheit. The sun's core is 1,000 times too cold. When physicists in the 1920s first calculated this, they were stunned. They ran the classical probability of two protons fusing at 15 million degrees. The number they got was effectively zero, not small, not unlikely. For all practical purposes, zero. The sun should not be shining. Fusion should not be happening. The stars should be dark. The universe should be cold and empty and dead. But look out the window. The sun is there. It is shining. Right now. So either the math is wrong and it is not, or something else is going on. Something that classical physics cannot explain. Something that breaks every rule you thought you understood about how objects move through space. This is where we meet a young man who asked a very different question. His name was George Gamow. He was 24 years old, and in 1928, he was sitting in a lecture hall in Göttingen, Germany, when staring at a problem that had been driving physicists insane. Radioactive decay. Certain atomic nuclei spontaneously spit out particles, alpha particles, with energies that made no sense. The particles came out with less energy than the barrier holding them in. By every classical calculation, they should have been trapped. Forever. But they were not trapped. They were escaping. Somehow. And nobody could explain it. Gamow looked at this problem and asked a question that nobody else was asking. What if the particle does not need to climb the hill? What if it does not go over the wall? What if it does not smash through the wall? What if it just appears on the other side? Not by magic, not by cheating in some vague, hand-waving way, but by a precise, calculable, mathematically rigorous mechanism that falls directly out of the equations of quantum mechanics. Gamow was not guessing. He was reading the math, and the math was saying something extraordinary. In the quantum world, things get jittery, things get fuzzy, and walls, even walls made of pure force, are not quite as solid as you think. Here is what you need to understand, and this is the part where most people get lost. Not because it is complicated, but because it is strange. In classical physics, Newton's physics, the physics of billiard balls and cannonballs and bowling alleys, a particle is a thing. A hard, solid, definite little ball. It has a position, it has a speed. It is either here or it is there. Never both. Never in between. Quantum mechanics says no. A particle is not a little ball. A particle is a wave. A smeared-out, fuzzy, probabilistic wave that does not have a definite position until you measure it. Let me show you what that means. Imagine you are standing on one side of a brick wall, a thick, solid brick wall, and you throw a tennis ball at it. Hard. What happens? The ball bounces back. Obviously, you throw it again. It bounces back 1,000 times, 1,000,000 times. It always bounces back. The wall is solid. The ball cannot pass through. End of story. That is classical physics. Now shrink the ball. Make it very, very small. Atom-sized. Proton-sized. And shrink the wall too. Make it an energy barrier. A Coulomb barrier. A wall made of electromagnetic force instead of bricks. In the classical world, nothing changes. Small ball, big ball. A wall is a wall. The ball hits, the ball bounces back. But in the quantum world, something different happens. The particle, remember, it is not a ball anymore, it is a wave. The wave hits the wall, and most of the wave bounces back. Just like you would expect, but not all of it. A tiny fraction of that wave leaks through. It does not go over. It does not smash through. It seeps through the wall like water seeping through a crack in a dam. The wave function, the mathematical description of where the particle might be, does not stop at the wall. It decays exponentially inside the wall, but it does not hit zero. And on the other side, there is still a little bit of wave left, a tiny vanishing sliver of probability, which means there is a tiny vanishing chance that the particle is on the other side. Not because it broke through, not because it climbed over, but because its wave function leaked through, the probability leaked. This is quantum tunneling. And I want to be very precise about that word, because the word tunneling is misleading. It makes you think of a mole digging a hole, of a prisoner with a spoon, of something physically boring through solid matter. That is not what happens. Nothing tunnels, nothing digs, nothing moves through the wall in any classical sense. The wave function simply exists on both sides. It was always there. The probability was always non-zero. A better word, and this is not the textbook word, this is my word, is leaking. Not tunneling, leaking. The particle leaks through the barrier, its probability leaks, its existence leaks, like a ghost walking through a wall, except it is not supernatural. It is mathematical. It is precise. And it is real. Gamow calculated the exact probability of this happening for alpha particles escaping a nucleus, and his numbers matched the experimental data perfectly. For the first time, radioactive decay had an explanation, a real one, a quantum one. And if a particle can leak out of a nucleus, maybe a particle can leak into one. Let us go back to our protons in the sun, the protons in the sun. Remember the problem. 15 million degrees Celsius, 27 million Fahrenheit, 1,000 times too cold. Two protons flying at each other at 500 kilometers per second, about 310 miles per second, and the Coulomb barrier throws them back. Every single time. Classically, the probability of fusion is zero, but the protons are not classical objects. They are quantum objects. They are waves, and waves leak. Here is what actually happens inside the sun's core. Two protons fly toward each other. They hit the Coulomb barrier. Most of the wave function bounces back, just like that tennis ball hitting the brick wall, but a tiny sliver of the wave function leaks through, seeps past the barrier, and on the other side, the strong nuclear force, that incredibly powerful short-range force, grabs hold. Fusion, energy, light. Not because the proton had enough energy to climb over the wall, it did not. Not because the wall was weak, it was not. But because in the quantum world, walls are not walls. They are filters, and some probability always leaks through. Now I want to be very precise about the numbers, because the numbers are what make this extraordinary. The probability of any single pair of protons tunneling through the Coulomb barrier and fusing is absurdly small, roughly 1 in 10 to the power of 28. That is a 1 followed by 28 zeros in the denominator. 1 chance in 10 billion billion billion. For any one pair of protons, on any one collision, the odds are essentially 0. But here is the thing about the Sun. The Sun is big. The core of the Sun contains roughly 10 to the power of 57 protons. So that is 1,000 trillion 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 protons, and they are colliding with each other billions of times per second. Each one. So even though each individual collision has almost no chance of fusion, when you multiply almost no chance by an astronomical number of attempts, you get something. You get the Sun. Not a lot of fusion, not an explosion, just enough. A slow, steady trickle of quantum leaking, happening trillions of times per second, across a core the size of, well, imagine a sphere about 150,000 kilometers across. That is roughly 93,000 miles, about a quarter of the distance from here to the Moon. And that trickle is the reason you are warm right now. Now here is something that should surprise you. You might think, okay, quantum tunneling makes fusion possible. So why doesn't the Sun just explode? If protons can leak through barriers, why doesn't all the hydrogen fuse at once? Because there is a sweet spot. And Gamow found it. It is called the Gamow peak. And it is one of the most beautiful calculations in all of physics. Here is the problem. 2 competing effects. Effect number 1. The faster a proton moves, the higher its energy, the thinner the barrier looks, and the more likely it is to tunnel through. So hotter protons tunnel more easily. Effect number 2. In any gas, most particles are slow. Only a tiny fraction are fast. The hotter the gas, the more fast particles you have. But even at 15 million degrees, the truly fast protons are rare. So you have a trade-off. Slow protons are common but cannot tunnel. Fast protons can tunnel but are rare. The Gamow peak is the energy where these 2 curves overlap. The narrow window where protons are just fast enough to have a reasonable tunneling probability and just common enough to matter. And that window is tiny. Razor thin. Only protons within a very narrow energy range contribute to fusion. Too slow, the barrier is too thick. Too fast, there are not enough of them. The sweet spot is about 6 kilo-electron volts. 6,000 electron volts. That corresponds to a temperature of roughly 70 million degrees, about 126 million Fahrenheit. Wait, 70 million degrees? But the Sun's core is only 15 million, exactly. The Gamow peak sits above the average temperature. Only the rare, unfast protons in the tail of the distribution, the statistical outliers, are the ones doing the fusing. And that is why the Sun burns slowly. Not because fusion is easy, not because the Sun is efficient, but because fusion is almost impossible. It relies on a razor-thin overlap between quantum probability and statistical luck. The Sun converts roughly 600 million tons of hydrogen into helium every second. That sounds like a lot. But relative to its total mass, 2,000 trillion trillion tons, about 4.4 thousand trillion trillion pounds, it is nothing. A rounding error. The Sun has been burning for 4.6 billion years, and it is barely halfway through its fuel. If tunneling were even slightly more probable, the Sun would burn through its hydrogen in millions of years instead of billions. Stars would flare and die before life had a chance to crawl out of the ocean. If tunneling were slightly less probable, Fusion would not happen at all. The sun would be dark, and you would not exist. Nature does not just cheat. It cheats by exactly the right amount. Let me put a number on exactly the right amount. Take a single proton in the core of the sun. One proton, it slams into other protons billions of times per second. Billions. And each time, the probability of tunneling through the Coulomb barrier is roughly 1 in 10 to the power of 28. So how long, on average, does one proton have to wait before it successfully fuses with another? About 9 billion years. Let that sink in. The sun is 4.6 billion years old, and any given proton in its core has probably not fused yet. Most of them are still bouncing around, waiting. The average proton in the sun will live its entire stellar lifetime without ever fusing once. That sounds like a failure. It sounds like a problem. It is not. It is the reason you are alive. Think about it. What if quantum tunneling were even slightly more efficient? If the probability were 1 in 10 to the 25th instead of 10 to the 28th, fusion would happen 1,000 times faster. The sun would burn through its hydrogen not in 10 billion years, but in 10 million. Stars would flare and die before complex life had a chance to evolve. And if tunneling were much more efficient, if protons fused easily, the sun would not be a star. It would be a bomb, a thermonuclear detonation the size of a solar system, over in a flash. Here is something that will bother you. A cubic meter of the sun's core, the hottest, densest, most extreme environment in the entire solar system, produces about 276 watts of heat. That is roughly 940 BTU per hour. You know what else produces about that much heat? A compost heap. A cubic meter of rotting leaves in your backyard generates roughly the same amount of energy as a cubic meter of the center of a star. You, right now, sitting there, are producing about 80 watts of heat. Your body mass is maybe 70 kilograms, about 154 pounds. The same mass of the sun's core produces far less heat than you do. You are hotter relative to your volume than the center of the sun. So why is the sun so hot? Not because its core is efficient. Its core is pathetically inefficient. The sun is hot because it is enormous. 2 million trillion kilograms, about 4.4 million trillion pounds, of mildly warm plasma, all stacked on top of itself, with nowhere for the heat to go. And that is the dual paradox. The sun is hot because it is cold enough not to explode. It is burning because matter is not solid. It is shining because quantum mechanics allows a rounding error. And that rounding error, multiplied by the sheer crushing scale of a star, is exactly enough to light up a solar system. Not too much, not too little, exactly enough. But I have told you that it happens. I have not told you why it happens, not the deep reason, not the way I would explain it. Let me show you my way. There is a way to understand quantum tunneling that goes deeper than the wave function picture I gave you earlier. It is called the path integral formulation, or as I prefer to call it, the sum over histories. It is a method I worked on for a long time, and it gives you a completely different way of seeing what nature is doing. Here is the idea. In classical physics, a particle moving from point A to point B takes one path, the shortest path, the most efficient path. You throw a ball, it follows a parabola. End of story. In quantum mechanics, in my formulation, the particle takes every path, every single one, the straight path, the curved path, the path that goes to the moon and back. Shot the path that zigzags through the atmosphere and loops around Jupiter. Every conceivable path from A to B, no matter how absurd, no matter how ridiculous, the particle takes all of them simultaneously. Now, how do you calculate what actually happens? Imagine this. Every path carries a little stopwatch, a tiny arrow spinning around a dial, and as the particle travels along each path, the arrow spins, faster for some paths, slower for others. When the particle arrives at point B, you take all the arrows from all the paths and add them up, head to tail, like vectors. And the total length of that final arrow tells you the probability of the particle arriving at B. For most of the crazy paths, the ones that go to Jupiter, the ones that zigzag through walls, the arrows point in random directions. They cancel each other out. They add up to nothing. But for the paths near the classical path, the sensible path, the one Newton would predict, the arrows all point roughly the same way. They add up, they reinforce each other. And that is why, in everyday life, things seem to follow classical rules. The crazy paths cancel, the sensible path wins, balls follow parabolas, planets follow orbits, everything looks normal. But here is where it gets extraordinary. When there is a barrier, a Coulomb barrier, an energy wall, a region that classical physics says is forbidden, some of the paths go through it. Not over it, not around it, through it. And those paths are not illegal. They are not cheating. They are mathematically valid paths in the sum over histories. The arrows from those paths are tiny, vanishingly tiny, but they do not cancel to zero. They add up to a small, non-zero probability. Quantum tunneling. Not a trick. Not an approximation. A fundamental consequence of the fact that nature explores every possible path, including the ones that look impossible. Now close your eyes, and just for a moment, point at the sun. You know roughly where it is. You can feel the warmth. Point at it. Right now, in the core of that star, octillions of protons are colliding, and for each collision, nature is summing over every possible path, every classical path that bounces back, and every quantum path that leaks through the barrier. The arrows from the tunneling paths are unimaginably small, but there are so many protons, so many collisions, so many paths being explored every fraction of a second, that those tiny arrows add up. They add up to light. They add up to warmth. They add up to the heat on your fingertip right now. The rules of allowed and forbidden are not absolute walls. They are suggestions. And nature, given enough time, enough particles, enough paths, finds every way through. That is what I wanted to show you. So let's bring this all together. We started with a question. Why is the sun not dark? And the answer turned out to be stranger than the question. The sun's core is 15 million degrees Celsius, about 27 million Fahrenheit. Sounds hot. But to push 2 protons past the Coulomb barrier, you would need 10 billion degrees, 1,000 times hotter than the sun actually is. Classically, fusion is impossible. The protons bounce off each other, every single time. But nature cheats, not by brute force, not by climbing over the wall, by leaking through it. Quantum tunneling. The wave function of a proton does not stop at the barrier. It decays, yes, but it does not hit zero. A tiny sliver of probability leaks through to the other side, and on that other side, the strong nuclear force grabs hold. Fusion, energy, light. The odds of any single collision producing fusion are 1 in 10 to the 28th, essentially zero. But the sun has 10 to the 57th protons, colliding billions of times per second. Multiply almost nothing by almost infinity, and you get something. You get the sun. And here is the part that should stay with you. If tunneling were slightly more probable, the sun would be a bomb. If slightly less probable, the sun would be dark, and you would not exist. Nature does not just cheat. It cheats by exactly the right amount. A rounding error in the laws of physics, multiplied by the sheer crushing scale of a star, is exactly enough to light up a solar system, to forge the carbon in your bones, the oxygen in your lungs, the iron in your blood. The rules of allowed and forbidden are not absolute walls. They are suggestions. And nature, given enough time, enough particles, enough paths, finds every way through. That is what I wanted to show you. Not just how the sun works, but how nature thinks. Nature is strange. It is far more imaginative than we are. If this changed how you see the sun, even a little bit, tell me in the comments. What clicked for you? What still feels impossible? Subscribe if you want more physics explained the way Feynman would have explained it. No memorization, just understanding. And I'll see you in the next one.